So, any problem involving rates, if we have related rates, we have to make sure that every time we do the derivative of a variable, it has be something dt. And the reason being, all of these are talking about your derivatives with respect to time. So the only variable that wouldn't have to have that was if we had a variable that was just t. Okay? So if we look at number 1, we have a snowball that is melting, so the surface area decreases 4 square centimeters per minute. So look at that, square centimeters, that's area, minute is time. So that's my dA dt. Decreasing, so it's -4. We want the rate at which the radius is decreasing. So we're looking for how the radius changes. So dr dt, that's my question mark. When the diameter is 39. Now, do I ever make any mention about diameter? So anytime, we never use diameter. Anytime I give you the diameter, what you really need to do is find your radius from that. And how do we get our radius? All right, just half of the diameter. So 39 over 2. Okay, and you're welcome to give a decimal as well. All right, so from there, we are talking about area. So area of a sphere, 4 pi r squared. I would give you that one if you needed it. So all of the stuff you've written down right now, yeah, those are steps that you could maybe skip, but those are easy points. You get points for just writing that stuff down. So even if you can't do anything else in the problem, you've earned yourself a couple points right there. Likewise, if you make a mistake later on and I don't have anything to recognize that you knew what your variable stood for, you lose those points, okay? So show me what you can. So derivative of a would become dt. Okay, the 2 comes down, so that's 8 pi r, but we did the derivative of an r, so it gets dr dt. So now we plug in. dA dt is -4 equals 8 pi times 39 over 2, and we don't know dr dt. So we would have to divide, so we would get -1 over 39 pi. And what are my units? So look back at this. R was the radius, so my radius was in centimeters. T is the time, and my time in this problem was minutes. So we get the amount the radius is changing. Square is area. So volume is always cubed, area is always squared, and just a regular length is always the first power. Anything else there? So number 2. We have a ladder. We've had a lot of these ladder problems. So we have the top of the ladder is sliding down vertical wall. So this part is coming down. And the bottom is going to be sliding away from the wall. So we need some variables here. You can call them whatever you want. So I could call this X and Y and Z. You could do A, B, and C. I don't care. That's part of why the picture is so important, so I know what your variables are. So if the top is coming down 0.15 meters per second. So here's the top. That measurement is Y. So if I'm talking about how it's changing, that's my dy dt. Since it's coming down, it's getting smaller. That's a -0.15. At the moment, when the bottom is 3 meters from the wall. Is the bottom always 3 meters from the wall? No, so I can't plug it in yet, but I know at some instant the x is 3. It's going to be sliding away from the wall, so I'm telling you how that changes at 0.2. We want to find out how long the ladder is. So anytime we have a triangle, the Pythagorean theorem has been very useful. So derivative of x squared would be derivative of y squared Z. Z is the ladder. Is that length changing? No, so it's a constant. So its derivative is 0. Okay, so at this point, I've got my x, I have my dx dt. I don't know my y, but I do know dy dt. Okay, so we get y equals 4. And now, I haven't answered the question. I wanted to know z, but we can go back. X squared plus y squared equals z squared. So 3 squared plus 4 squared equals z squared. So the ladder is going to be 5 meters long. Is that okay for that? Okay, if I'm doing a problem and you're confused and you need another similar one, let me know. So you'll probably have something, at least one, if not a couple, that involves Pythagorean theorem on your test, because we've done that a lot. Just keep in mind, anything that's a constant, its derivative is 0. But if it's changing, you can't plug in your numbers until after the derivative. All right, number 3, we have another triangle problem. The altitude of a triangle. Okay, so I didn't tell you what kind of triangle, so you may have drawn a right triangle or something. The altitude is the height. So I'm going to call that dh dt. Is changing at a rate, it's increasing, so it's a positive 3. The area is increasing, so it's a positive 4. We want to know how the base is changing. Okay, so the base is like our bottom. At the moment when the altitude or the height is 10 and the area is 90. So I've drawn a picture, I have labeled all my numbers, and I've shown I know what those represent and I know what I'm looking for. If I'm talking about area, what's area of triangle? Alright, don't forget your basics here. This has 2 variables, so if you do this derivative, you have to do the product rule. So derivative of the first would be 1/2, derivative of b would become db dt times the second plus the first, derivative of the second. Derivative of h would be dh dt. So plug in what we know. We have 4 plus 1/2. I don't know db dt. H is 10. Okay, I don't know the b, but I really need it to be able to solve this problem. Is there any way I could find my base at this instant? Yeah. So I know the area is 1/2 base times height. So if the area is 90, so the base is 18 at that instant. We have only 23/5. B was the base, which is measured in centimeters. T was time. So the base is actually getting smaller at that instant. Is this helping, guys? Going through them and talking through, practicing notation, what I expect. Make sure you're writing out your formulas before you do the derivatives. I know where everything's coming from. Number 4, we have a balloon. So our balloon is rising at a constant speed of 5 feet per second. So if I'm telling you how that's changing, that's got to be a variable. So if I call that, say I call that y. If I'm telling you how that's changing, that's my dy dt. Everybody's embracing. Are you changing your variables to match mine? They can be whatever you have them to be. The second one, we have a boy that is cycling along the road. So if I have him writing down here, that has to be a variable. So if I call that x, so his speed is 15. At the moment when he passes under the balloon, it's 45 feet above him. How fast is the distance between the boy and the balloon increasing 3 seconds later? So I need to know how this is changing. So we are looking for dz dt. At the moment in question, we need to know what our variables were. All right, so when he was directly underneath it, the balloon was at a height of 45. But I went 3 seconds later, and what do we know about this balloon? It goes up 5 feet every second. So in 3 seconds, how much did it go up? 15. So my total height is now 60. Okay, when the boy started, he was directly underneath, so my x was 0. But now he's been pedaling for 3 seconds, and we know that in 1 second he goes 15, so how far has he traveled? Okay, can we find the hypotenuse at that given point? So 45 squared plus 60 squared equals z squared. What do you guys get for that? 75. Is it okay if I skip the work and try to work that out? Okay, all three of those measurements are changing. So we can't plug them in yet. But now we go to our Pythagorean theorem and we do our derivative. So derivative of x would be 2x dx dt. Derivative of y would be 2y dy dt. Derivative of z would be 2z dz dt. So plug in. X was 45, dx dt is 15, y is 60, dy dt is 5, z is 75, dz dt. Okay, and what's that work out to be? Let's just skip to the answer. You guys can do the math there. What'd you get? And z was in feet, and our time here was in seconds. So their distance between them is increasing 13 feet per second. All right, so if I gave you, we've had some kind of like involving these rates before. I think we had a couple like with cars moving, that they're starting at the same point and driving, something like that. So we've done some of those before. Let's look at number 5. Okay, we've done several of these, so you can probably expect a very similar one on your test. We have a funnel in the shape of an inverted cone. So it's just an upside down cone. It is 30 centimeters deep, so overall my height is 30. And the diameter is 20, but do we ever use diameter? No, so that means my radius is 10. Okay, liquid is flowing out of the funnel, so it's coming out. 12 cubic centimeters per second. If I'm talking about cubic, what am I looking at? Volume. So my dV dt, if it's coming out, then my volume would be negative. At what rate is the height decreasing? So I'm looking for how the height is changing. At the instant when the liquid is 20 centimeters deep. So the 20 is my height. Okay. So if we're talking about volume, this would be a formula I would give you. 1/3 pi r squared h. What is the problem if I try to do this derivative right now? The r. Did I give you any information about the dr dt? I didn't tell you what it is, and it's not the one I'm trying to find. So I really don't want it there. So before I do this derivative, I need to figure out, is there something else I could use in place of that radius? So how do we do that? We think of similar triangles. Okay, my whole cone, this is the radius and that's the height. And we know our actual radius is 10 and the height is 30. So you can say like r over h equals 10 over 30. So we're trying to solve for r. So you can just multiply over your h. So the radius is 1/3 height. Okay, so let's clean it up before we do the derivative. 1/3 squared is 1/9, so it would be pi over 3 times 9 is 27. H squared times h is h to the third. So our derivative, dv dt, equals 3 comes down, so that's pi over 9. H squared, what's the derivative of h? So then we plug in our stuff. So anytime, we've seen it a lot with these cone problems. We've also had some with like rectangles where I might give you how the width is changing but not the length or something like that. If you don't have any information about it, try to get rid of that variable before you do your derivative. So, I do dt, negative 100 pi. H was measured in centimeters. Time was in seconds. And you can also tell a lot, it should be reasonable. If our volume is getting smaller, then the height should be going down. So we should expect a negative. And watch for those things. And I brought this 3 down. Be 3 pi over 27, which reduces to pi over 9. Any others? Alright, this was a homework question. The circumference of a sphere, or I should say I changed the numbers, but it was close to a homework question, was measured to be 90 centimeters, and the error in the circumference was 0.5. Use differentials. Whenever you see differentials, that means I'm no longer doing rates, so everything doesn't get to be something dt. We're doing normal derivatives, but the differential is just the dy part, okay, when you multiply over that dx. So we want to estimate the error in volume. So volume is 4/3 pi r cubed. So if we do this derivative, the derivative of volume would be in terms of r, so dv dr. 3 comes down, subtract 1 from the power. So my differential, my dv, is 4 pi r squared dr. There's that part. So I need my r and my dr. Those were not what I gave you, but we know circumference is 2 pi r. So if 90 equals 2 pi r, divide by 2 pi, so my radius is 45 over pi. Okay, dr. If we did this derivative, we would have dc dr equals 2 pi. so the DC is 2 pi dr. But I told you DC was 0.5. So 0.5 divided by 2 is 0.25 over pi is the dr.
Wait, why is DCDR pi? I mean 2 pi.
This is, so it's 2 pi r, so 2 pi is just a coefficient derivative of r, which is v1. So then if you work that out, it comes out to be approximately 205.175. Volume is cubed, so cubic centimeters. So that would be our error in volume, or the differential. When you're looking over this stuff, guys, there will be 1 or 2 questions about differentials and linear approximations, but my focus is really going to be more on those related rates. You know, if you think time-wise, we spent a long time on those, and we were only on this last section a couple days. So you can probably expect a question or 2 with a linear approximation and differential, but most of them will be the others.
Oh, why did DC end up being 0.5?
It was given in the problem.
So
it
that's
told us the error in that. Okay. Number 7. We're doing linear approximation. So we are essentially trying to write the equation of the tangent line. Okay, it's a square root, so we could write it as a 1/2 power if we preferred, whatever you like. Our a is -2, so if you plug -2 into this, what do you get? 3, because it becomes 7 plus 2, which is 9 squared minus 3. So that's my point. To write the equation, we need a point in the slope. So we need the derivative. Exponent comes down, inside stays the same. Subtract 1 from the power, times derivative of the inside, which is, so we have a -1 over 2 square root of 7 minus x. So to get our slope, we need to know what the derivative is at -2. So if we put in a -2, we get a -1/6. So now we have a point in the slope. We need to do our equation. All right, so plug into y equals mx plus b. So we get 8/3. So the linear approximation is -1/6x plus 8/3. Okay, am I done? No, I wanted you to approximate at 7.1. So we have to watch. Remember, the equation is the square root of 7 minus x. And we are trying to approximate the square root of 7.1. What is my x? -0.1. Okay, because this had the 7 minus x under the radical. So if you say 7 minus x equals 7.1, it wasn't just an x under the radical. That's why we're not just plugging in a 7.1 to this equation. So if we put that in, I don't know what that is as a decimal if you're checking yourself. because the equation, the original function, was not the square root of x. It was the square root of 7 minus x. So if you need the square root of 7 minus x to equal the square root of 7.1, you have to figure out what x is. All right, so number 8, one more linear approximation. We want 83 to the 3/4. So first we need a function. We need something to the 3/4 power. Our a value is something close to 81 that we could work out. Keep in mind, a 3/4 means you have the 4th root of something cubed. Okay, so we need something that we can easily do the 4th root of. So think about things to the 4th power. 2 to the 4, 64. Is it? 2 times 2 times 2 times 2 is 16. Is that close to 64? Or to 83, sorry. No. So 3 to the 4th is 3 times 3, 9 times 3 times 3, 81. Is that close to 83? Yes. So that's the x value we would use. The 81 for our x. And then the 4th root of that would be 3, the 3rd is 27. So 81, 27 is our point. So then we need our slope. Okay, if you need to rewrite it, that's like 3 over 4 and so 4 through the x. To get our actual slope, now we plug in our 81. 4th root of 81 is 3, so we get 1, 4. So now you write your equation, y equals mx plus b. All right, so if you do that, we get the linear approximation to be 1/4 x plus what? So now we can approximate it. This equation was just x to the 3/4, so we can put in the 83. So 27.5. So linear approximation. Essentially, write the equation on the tangent line, and then we had to plug in that value. Is that okay?
For the order pair, how do you get 27?
If you put 81 in for your x. So that was the 4th root of 81 to the 3rd. 4th root of 81 is 3 to the 3rd. Other questions there? Number 9, a differential. You can probably expect me to put something with a log on there. We've been seeing a lot of logs recently. So I might ask you to do a question very similar to that, a differential with a log. So a differential is basically start with the derivative. So this would be dy dx. Derivative of a log is 1 over the argument. But what do we have to do after that? Yeah, chain rule, derivative of the inside. So derivative of x is 1. The square root is like a 1/2 power. So the 1/2 comes down, inside stays the same, subtract 1 from the power, times derivative of the inside would be 2x. So the thing that makes it a differential is at the very end, you multiply that dx over. This one, it's just ugly, so there's not a lot of cleaning up we're going to do. You would have 1/2 times 2x is x. If you wanted, you could put that square root on the bottom. But that's really all you could do. That one was just fairly ugly at the end.
So dy is our
Differential is the dy, yes. So do your derivative, multiply the dx over. All right. So I've given you a lot of kind of indicators so far what's going to be on your test. It's a lot of related rates problems. How we have a differential, how we have a linear approximation. Section 3.7 was the applications. So the two main ones there was the cost problems and like our velocity problems. So we'll probably have some of those. So let's look at that now. Number 10. So we know our cost equation. Marginal cost is what? So we get 2 minus 0.04x plus 0.00021x squared. C prime of 100. We're just plugging in 100 into this. Okay, and I'm not going to take the time to do that. What do you get when you plug in 100? 0.1.
Yes.
So then the interpretation, marginal cost, a derivative is a rate of change. So the derivative of cost doesn't tell me what the cost is, it tells me how the cost is changing. So 100 is how many items we have produced. So it's saying when 100 items are produced, the cost is increasing. $0.10 per item. Okay, so you have to have the 100 in there because is the marginal cost going to be the same when 200 items are made? No, probably not. So it's saying when I make 100 items, I would expect if I'm going to make another item, it would cost me an additional 10 cents. Okay. So part C, I want you to compare that with the actual cost. So I need the actual cost of making 101 items. So if we plug that in, is this all I need? No. B was telling me how the cost was changing. So I need to figure out how much did the cost actually increase. So you have to plug both 100 and 101 into the original cost equation. So when you subtract those, the actual cost increase so our estimate was pretty close. Okay, that's telling us the true cost. Our derivative was our estimate for the cost. Yeah, Emily? Huh? Oh, did I? Which one did I write down on? First one? 990. Thank you. Other questions there? So number 11, a vertical motion. You notice 10 and 11, math-wise, they're not that hard. The derivatives are basic polynomials. The thing that I'm testing on those questions is really your understanding. Do you understand what the derivative is? Do you know when to apply it? So it's not so much some crazy calculus that you're doing, it's just understanding derivative is the rate of change. So when I look at this one, how do we find velocity? And I asked for the velocity after 2 seconds, so if you plug a 2 in there, you get 7.56 meters per second. All right, maximum height. This one we struggled with. If you have your maximum, so think about this, it's going up and coming back down. Where does your maximum happen? Right here. What's true right there? The derivative is 0. So we take our derivative that we just found and set it equal to 0. If you do that, you get not a pretty answer. Let's go ahead and do fraction. 125 over 31. But I didn't ask the when, I asked what's the height, so now what do we do? Right, and so if we put that in, we get 30.24. Right. What is the velocity of the rock when its height is 25 meters? So the height is 25. So if we set that equal to 0, okay, so we're trying to figure out when this is 0. Obviously, this one is not very pretty, and on a test without a calculator, I would have to give you something that you could factor. If we can't factor here, what could we do? Quadratic formula. So we get times of 2.35 and 5.71. So I wanted the velocity going up and down. We have found the times. Which one of those is going to be going up? Right, because we started on the ground, we threw it up, and then it came back down. So you're going to your velocity equation and plugging those in. So that was your derivative from part A. And notice here I get a positive velocity because it was going up. Coming back down, you plug your second time into your derivative, and we get a negative because it was coming back down. Part D. We want to know when it hits the ground. So if it hits the ground, the height is 0. So we could factor out a t. Set those equal to 0, and we get t equals 0 and 8.06. Which one of those would be when it hits the ground? Acceleration, how do we get that? Second derivative. So we take our derivative of our velocity, or second derivative of the original, and we get negative 3.72. And the final one, what's the velocity at the time when it returns to its starting position? So we need the velocity when it hits the ground. And in part D, we found it hits the ground after 8.06 seconds. So we just plug that time into the derivative, and we get a negative 14.9. I know I didn't really show all my calculations there, but does everyone understand how I'm getting my numbers? So it's a matter of knowing, am I plugging this into the original, the derivative, where does it go? So a company makes computer chips from square wafers of silicon. So we have a square. What do you know about a square? All sides are the same. If we keep reading on, we want to keep the side length very close to 15 millimeters, and we want to know how the area changes when the side length x changes. So my side length is x, and we want that to be close to 15, but we know it's not perfect. We know we can be off. So I want to know, how is the area going to be changing when my side is 15? So area, length times width, would just be x squared. If I'm wanting to know how it's changing, what do I need to do? Derivative. So a prime is 2x. We're looking at the instant when x is 15. And a prime is 30. And so then I want to explain its meaning. So when the side lengths are 15 millimeters, the area is increasing 30, and area would be squared. So square millimeters.